Welcome to Math 146 Statistics. I'm excited about our journey that we're going to take together over the next several weeks. This video and the videos that come are meant to introduce the topics to you, and where they really are going to start to become concrete is with the in-class activities. So make sure you're coming to class on time to participate in those in-class activities. So today we're taking a look at Chapter 1 in your textbook, which looks at sampling and data. And the essential question that we're going to attempt to answer today really is the big question: what is statistics? We're going to cover a lot of introductory vocabulary that's going to be essential that you understand and know how to use in this chapter and also in the chapters that are coming. So today is going to be a little bit drier in that it focuses a lot on vocabulary. I promise the videos will get more interesting as time goes on. But first, let's define statistics. Statistics is basically the collection, analysis, interpretation, presentation of data. And we're going to get to do a lot of this throughout the course. Just a really basic, simple example to set this up, though. Let's take a look. Let's say we did a survey and found out the number of hours of sleep students were getting per night. And when we did that, we got data of 5, 5.5, 6, 6, 6, 6.5, 6.5, 6.5, oops, 6.5 I said, 7, 7, 8, 8, and 9. And one way that we can interpret this data is we could make maybe something called a dot plot, which is going to go through, we're going to make this number line here, starting at 5, 6, 7, 8, 9, maybe 10. That's going to represent the number of hours of sleep they got. And we'll put one dot for every data value. So there's a single 5, we'll put a dot for 5. There's a 5.5. Notice there's 3 6s, so we'll put 3 dots for 6. There's 3 6.5s, so we'll put 3 dots for 6.5. There's 2 7s, 2 8s, and a single 9. And so now we've collected and analyzed the data, we're ready to interpret it. Maybe we could ask the question, where is the data clustered? And we could ask the question, what does this mean? Well, you'll notice there's this kind of clumping of data right here between 6 and 7. Most of the data is right there. So it's clustered around 6 to 7 hours. This then means, if it's clustered there, it means most of the data is there. It probably means most students get 6 to 7 hours per night. Now this was kind of a loose statistical process here because we just kind of said, hey, they're grouped here, so must be most students fall within that range. The rest of this course is going to look at a more mathematical way to make that conclusion, or maybe say we don't have enough evidence to make that conclusion. Either way, that's kind of an intro of what statistic is and what we're going to do. There are actually two areas of statistics that we are going to look at in this course and that exist in the entire field of statistics, if I don't scroll away everything. The first area is what we call descriptive statistics. And descriptive statistics will organize and summarize data. And that's what we're going to really look at here in chapters 1 and 2. Chapters 1 and 2, we're going to organize and summarize a lot of data to begin to set up what is called inferential statistics. And inferential statistics is really the formal process for drawing conclusions from data. And this formal process is what we're going to look at when we get to chapters 8 through 13. Well, what about the middle? What about chapters 3 through 7? Well, this formalized process for drawing conclusions from data is really based on the rules of probability. So in order to do that formalized process, we need to understand those rules of probability, and that's what we're going to look at in chapters 3 through 7. So that's kind of an outline for the entire course of what you're going to see. Now, as we work through the statistics and we analyze data, we describe it, we make inferences based on the data we collect, we need to make sure we understand what are called the different levels of measurement. Because we need to understand the level of measurement we're taking in order to know what calculations we're allowed to do. The most basic, simple type of measurement is what we call a nominal measurement. And that's basically splitting up your data into categories. You know, a category might be we look at the color of car you drive. You drive a red car, I drive a blue car, he drives a green car, she drives a teal car. With nominal categories, we can't do math with that. We can't find the average color car and get a blue point green car on average. Categories we can only do very few simple things with. We can find the one that occurs most often. We can talk about how much more often it is, but we can't do a lot of math with the categories themselves. So that's why we have this next level of data, which is slightly more involved. It is called ordinal data. And ordinal data is data which can be ordered. An example of this might be the top 5 parks in the USA. These top 5 parks are ranked. There's the number 1 park, the number 2 park, the number 3 park, the number 4 park, the number 5 park. You could say the number 1 park is 2 ranks better than the number 3 park. So we can start to compare which one's more and less. But we really have to be careful because there is no scale. We can't say the number 1 park is, 3 better than the number 2 park. There's no scale. The space between them is not the same. The number 1 park might be significantly better, and 2 and 3 are kind of clumped together. There's no scale to separate them. They're ordered, there's just no scale. When we get that scale, we're now starting to talk about what is called interval data. Interval data, you can see a clear difference between data points. An example here would be temperature. In degrees Fahrenheit or degrees Celsius. There's a clear scale. 5 degrees is 10 degrees less than 15 degrees. A degree is always the same size. The space between 80 degrees and 81 degrees is the same as the space between 5 degrees and 6 degrees. It's the same space. We didn't have that when we were ranking the parks because one might be significantly better than the rest, which are clumped together. We lost that scale. With interval data, we have that scale. What makes interval data unique, though, is there is no absolute zero. And therefore, there is no ratio. Yes, there is a 0 degrees Fahrenheit, but why does it have to be where it is? Mr. Fahrenheit could have just as easily picked a different place and called that 0. Just like Mr. Celsius picked freezing water to be 0. No reason, just he had to have a foundation, so he picked one. There's no absolute. An absolute 0 would be 0 regardless of the units. Fahrenheit and Celsius and Kelvin have different zeros. Kelvin actually does have an absolute 0, but they have different starting points. When we get that absolute 0 starting point, we're starting to talk about ratio data. And ratio data has that absolute 0 point, where we have literally nothing. 0 degrees Fahrenheit does not mean there's no temperature. It's actually a measurement on the scale. But if we're talking about maybe your score on a test, now 0 does have an absolute point. 0 means you got absolutely none of the problems right on the test. That would be a 0 on the test. And the advantage of ratio data is when we have that absolute 0 point, if you compare somebody with a 20 to somebody with a 40, the 40 is literally twice as good as the 20. We can double it. This idea of doubling makes sense when we have an absolute 0. It does not make sense in interval data. We can't say 15 degrees is 5 times as warm as 5 degrees. They're both cold. You can't really be 5 times as warm or half as cold. That doesn't make sense in temperature. It does when we're talking about scores on a test, though. That's ratio data. So those are our 4 levels of measurement. As we take measurement, we need to make sure we're familiar with some key vocabulary. I told you there was a lot of vocabulary today. This is just one section of it. Key vocabulary as we're working with our statistics, when we're talking about the population, we are talking about the entire collection. Everybody. So if we're doing a study on college students, the population would be college students, meaning all of them. What we're going to be interested in statistics more often, though, is what is called a sample, or a portion of the population studied to gain information about the population. So if we're talking about all college students as the population, a sample would be 30 random students, or 30 random college students, I should say. So that's a sample of the entire population. And we'll talk about this idea of random in a little bit. So we collect a sample, these 30 random college students, and then we will calculate what is called a statistic, or some property of the sample. Maybe of our 30 random college students. So I'll say of the 30, average cost of books is $240. That $240 is not talking about average college students spend $240. 240 is a statistic because it's just talking about the sample, the 30 students we interviewed. Now, if we want to talk about everybody, what we'll talk about is a parameter. And a parameter is a property of the population. So here we could say the average college student spends $180 on books. Notice it's different than the sample because the sample might not have been truly random and it wasn't representative of our population. Our sample had an average of 240, but we picked a group of engineers who have very expensive textbooks and materials. In reality, the average college student is spending $180, so they're different. Is that significant? What does it mean? That gets into what we call hypothesis testing and inferential statistics, and we'll take a look at that in the second part of this course. One more vocab word, though, before we move on, and that is a variable. A variable means something very different in statistics than it means in normal algebra class. A variable is the characteristic of interest in our study. Here we're talking about cost of books. So the cost of our books is our variable, our characteristic of interest as we study this sample from the population and get a statistics which we hope is representative of the parameter. We're going to throw a lot of this vocabulary around. It's important that you know which group we're talking about. When we say statistic, we're talking about the sample. When we say parameter, we're talking about the population. And what we're measuring or asking about and counting is the variable. Speaking of measuring things, what we're measuring is called data. And data can come in one of two forms. The first type of form of data we can collect is what is called qualitative data. Qualitative data, notice it begins with the word quality, qualities of the data. We're talking about categories or characteristics, qualities of the data. An example of qualitative data that falls into categories would be something like blood type. You have O, A, B, AB. Blood type falls into categories. It is qualitative. There is no number assigned to it. The other type of data is quantitative. Quantitative data is data that we can count or measure. There's a number associated with qualitative data. You get a number of 7. You get 4.2. You get some quantity. Quantity. Quant means a number. Your data comes in numbers. And actually, quantitative data can be split into 2 categories as well. The first category of quantitative data would be discrete. And discrete data is countable. An example of discrete quantitative data might be the number of phone calls. A call center receives. That's discrete quantitative. It's a number, it's countable, it's discrete. What's important about discrete is you're not going to get the in-between values. You're not going to get 6.2 phone calls. You either get 6 or you get 7. It's discrete. You jump from one value to the next. And that doesn't necessarily mean whole numbers. It could be 5, 5.5, 6, 6.5, but we're missing the in-between values. You can't get 5.1238. Discrete is countable. The opposite of discrete, then, would be continuous. And that is a value that is measured, which means we do get all those in-between values. If the discrete data point is the number of phone calls, the continuous value might be the length of the phone call. Because you could have a phone call that is 7.289 minutes. You can get all those in-between values because time is continuous. We can have any amount of time we want, any decimal, any fraction, any whole number. That's continuous. Discrete number of phone calls, we can only have integer phone calls, actually natural numbers, because you can't even have negative. 7, 8, 9, 10. You're not going to have the in-betweens. So once we collect data, we need to start to display data. And there's lots of ways we can display data. We're just going to talk about a few of them right now and a few more as the course goes on. One way we can display data is in a pie chart. In a pie chart, the categories are wedges in a circle. So let's say we did some data and we said, what is your favorite season? Fall, winter, spring, or summer? And 3 people picked fall. Let's say 3 people picked winter, 6 people picked spring, and 12 people picked summer. So there's 24 total, right? So if we were going to make a pie chart for this, we would do a circle. And 12 of them liked summer. That's 12 out of 24. That's half of them liked summer. So we could even say that's 50%. 6 of them liked spring. Oops. So that's 6 of them, 6 out of 24, that's a quarter. That's 25% liked spring. And then 3 liked fall and winter. That was half of each of those. So that's 12.5% like winter and 12.5% like fall. So there we have a pie chart where each slice represents the proportion. You can see most people like summer. There's no school and no homework. What a wonderful season of life. We could also have represented this information in a bar graph. And a bar graph just has categories in bars rather than parts of a pie. So, we can do fall, winter, spring, summer, and then fall has 3, winter also has 3, spring has 6, so it's twice as tall, and summer has 12, so it's twice as tall, and there's a nice little bar graph. A variation on a bar graph, which isn't too exciting with this example, is what we call a Pareto chart, if I can spell it right. P-A-R-E-T-O. And it's a special bar graph where the bars are sorted largest to smallest. So in this case, I'm saying it's boring because they're pretty much already in order. We just need to switch the order of our chart. Put summer first because that's the tallest bar. Then we'll put spring next because that's the next tallest bar. And then tide would be winter and fall because those are the next tallest bars. So the Pareto chart, they're just in order largest to smallest. All right, drawing graphs, that's more of a K-12 thing. We're going to be really interested, though, in this part, the different types of sampling. When we collect data from a population, it's way too expensive and takes way too much time to ask everybody in the population a question. So instead, we're going to do a sample to find a statistic that hopefully represents the parameter of the population. The goal, as we collect this sample, is to be reflective of the population. Essentially, what we're asking is that things be random. So, how do we accomplish random sampling? Well, there's actually quite a few ways that we can go about collecting a random sample. Let's say that we're interested in college professors. And we're going to do a study of college professors, and so we need a sample of college professors. We could use what's called simple random sampling. And simple random sampling simply says each is equally likely to be chosen. So, for our example, maybe we put all the names in a hat and draw a number. Or I shouldn't say draw a number. We draw names out of the hat. So it's kind of random. Everybody's name is in there. We randomly pick out one person. Okay, Salah Abed. We randomly pick out another name, Chris Riley. We randomly pick out another name, and we randomly come up with this set of faculty for our sample. That's kind of the old school way. Kind of a newer way that we do this now is we assign each a number and use a random number generator. And fortunately, you have a random number generator on your calculator. So let's take a look at that. On my screen here, I have a TI 84 Plus Silver Edition calculator. For this class, you can use either an 83 or an 84. They're very, very similar. And we're only going to use the features that are the same between both of them. And if you have Plus or Silver or anything like that, it's basically the same calculator. The way we can get a random number is we hit the Math button. It's on the left side, third button down. And it gives us these menu options. The last menu option we can scroll over to is probability. And under probability, you will see the option for random int. Select random int, and it's going to ask us what range we want the random integers to come between. Let's say we have 30 faculty members to choose from, so we want a random number from 1, 30. Close the parentheses and hit enter. So we pick faculty member 29. Every time you hit enter, it's going to give you another number. Let's do 28. Then 5. Then 16. Then 13. And it's just going to give you a random number from that range, from 1 to 30. So that's one way we can get random people, is to just simply assign each a number and use a random number generator to come up with all of our options. That's simple random sampling. Another option is what is called stratified random sampling. And what stratified random sampling does is it looks at each individual strata, or each individual group. The population is divided, let's actually say, let's divide the population into groups. And take a proportionate sample from each group. So the way this would work is we would maybe divide our faculty into departments. And take a random sample from each department. So we take a random sample of a math department, take 2 random people from the math department. We go to the sociology department. We take 1 random person from the sociology department. We go to these very large departments and we'll maybe take 4 out of that department. And each department gets a random group selected from it. That is stratified random sampling, which is very close and easy to confuse with what is called cluster sampling. Which sounds very similar because we're going to divide population into groups again, and we call these groups clusters. And randomly select entire groups. So, for example, with our faculty that we've been trying to sample, we are going to split into departments, divide into departments again, and randomly select entire departments. In other words, with stratified, we split into departments and said, give me 2 random mathematicians. With cluster sampling, we divide into departments and say, hey, we selected the math department, we're going to take the entire math department. That's the difference between clustered and stratified. Stratified, we randomly select from the groups. Cluster, we randomly select entire groups. Another very common form of sampling is called systematic sampling. And this is, we follow a system to randomly select our people. We are going to randomly select a starting point and take every nth value after it. So for our example with choosing faculty from the population of college faculty, we randomly select, we put the names in alphabetical order, maybe. Then we will choose a random starting point. Probably use our random number generator to get the first one. The screen keeps jumping around on me. Sorry about that. Choose a random faculty, and maybe every 12th name after. So we go down the list 12 names and select that person. Down the list 12 names and select that person. If we get to the end, we go back to the beginning and keep counting until we get enough people that we want. So it's kind of random, but there was a system to that random sampling. The last type of sampling is used a lot, and it's not actually random, so we kind of frown upon it in the statistics community, and that is what is called convenience sampling, where we pick results from readily available groups. So, for example, if I'm doing a statistical study on faculty members, I decide to pick the faculty in my building, because they're close by. I can get to them quickly, I see them often, I can get data from them. So for convenience, I'm going to pick the faculty in my building, but what's important to note is this is not random. And so I could end up with skewed data. If I only interview the scientists and mathematicians, we're going to get a very different view of how the college works than if we interviewed the sociologists and the historians and the professional technical programs such as aviation or the nurses. Not random. Convenient sampling is kind of frowned upon, but it is done a lot in research, unfortunately. So we have one last thing to take a look at. This last thing, after sampling, we take a good sample. We're interested in frequencies, or the number of times a value appears. And with frequency, we might break it down. We're actually interested in not the number of times. If I tell you I did a survey and 48 people like chocolate donuts, that doesn't tell you much about the preference of chocolate donuts. That just tells you 48 of those I interviewed. So did I keep asking until I got 48 people? Or did the first 48 all say, yep, chocolate donuts are a good thing? So more useful than frequency is often what is the relative frequency, or the proportion of times a value appears. Basically, what we're doing is we take the number of times it appeared divided by the total in the survey. And then often what we're interested from there is what is called the cumulative relative frequency. The cumulative relative frequency is the sum of all previous frequencies. And this is going to lead into our discussion of percentiles in our next chapter. But cumulative relative frequency is what percent or proportion have this many or less. So let's do a quick example before we wrap up this video. Let's say I asked several college students the number of hours of work per day that they do. Maybe they got that part-time job at Subway and they want to know how often they're working. Well, here's the data that I got. 5, 6, 3, 3, 2, 4, 7, 5, 2, 3, 5, 6, 5, 4, 4, 3, 5, 2, 5, and 3. So we're going to make a frequency table that shows the number of times that each value occurs. We're going to find the relative frequency, so we can start to talk about the proportion that picked that. And then the cumulative frequency, the proportion that had that value or less. Looking at my list, I see, so first we'll maybe list out the values. I see we've got some that have 2 hours of work, some have 3, some have 4, some have 5, some have 6, and some have 7. In the frequency table, we only need to list the values that occur. We don't need to list everybody. And so when we do frequency, let's see, how many 2s occurred? 1, 2, 3 2s. So the frequency of a 2 was 3. How many 3s occurred? 1, 2, 3, 4, 5 3s. How many 4s occurred? 1, 2, 3 4s. How many 5s occurred? 1, 2, 3, 4, 5, 6 5s. How many sixes? 1, 2 sixes, and finally a single 7. So now we've got our frequencies. But again, frequency, whoops, not 7 sevens, we had 1 7. Sorry about that. Now that we have our frequencies, those don't mean much to us unless we know how that compares to the entire population. So that's why we look at the relative frequency. And the way we're going to get the relative frequency is I'm going to go to my calculator and say, well, how many total people were there? 3 plus 5 plus 3 plus 6 plus 2 plus 1. There's a total of 20 people in the survey. So the value of 2, we had 3 out of 20. So when I do 3 divided by 20, we get 0.15. The value of 3 occurred 5 times. 5 out of 20, that relative frequency is 0.25. 3 out of 20, that relative frequency is 0.15. 6 out of 20, that relative frequency is 0.30. 2 out of 20, that relative frequency is 0.10. And 1 out of 20, that relative frequency is 0.05. Now, if we're interested in also the cumulative relative frequency, we're just going to add up everything as it goes down. So first, the value of 2, there was 0.15, or 15%. 3 or less would be 25 plus 15, which is equal to 0.40. 40% had 3 or less. 4 or less would be 0.15 plus 0.45 is 0.55. Add 0.30, we get 0.85. Add 0.10, we get 0.95. And add 0.05, we get 1.00. We don't really need these lines in the middle. And so now we have our cumulative relative frequencies. We could say 85% work 5 hours or less. We can see this information quickly off of our table. So that's the end of Chapter 1. Chapter 1 is a lot of vocabulary. A lot of what does this mean? How do I use it? You want to take a look at the homework assignment that's been assigned to you in the book. We'll also work through some practice assignments and labs to kind of get used to using this vocabulary. We want to be very comfortable with it before we get into more of the mathy chapters, starting with Chapter 2. So take a look at it, and we will see you in class to mold this information a little tighter.